Hello, ladies and gentlemen. Welcome to Lecture 7. We're going to talk about learning here. We're going to review conditioning, which, of course, means what it sounds like. It's changing, like an air conditioner changes the air. Conditioning is going to change behavior. We're going to go through classical conditioning, which is a more passive form of learning, and then we're going to go through operant conditioning, which involves shaping behaviors with rewards and punishments. We talked about these in Lecture 1, and they're back. And then we'll talk about some other forms of learning besides conditioning that involve watching others. Okay, let's go through classical conditioning here. Pavlov's dog should come to mind. In classical conditioning, what we're going to do is take some stimulus that's meaningless or neutral, and we're going to associate that with some meaningful stimulus so that we will now respond to the neutral stimulus. All right, just like Pavlov's dog, you pair a tone, which really means nothing to a dog. A dog never salivates in response to a tone, but they always salivate in response to food. So by pairing the tone with the food, the tone can then elicit salivation. Okay, this is kind of learning cause and effect. When you hear the tone and you're presented with food, you then learn that the tone is going to lead to food, so you should start salivating. So in conditioning, we're just changing our associations. We're learning that the bell means food, or really it could be any two things. The one that we often encounter would be food poisoning and food aversion. Oftentimes, you will find a number of Chinese buffets around town. They're usually delicious. They're a great value. And so almost every time after you enjoy the Chinese buffet, you're going to feel good about yourself. It was great. It was cheap. And who doesn't love fried, sweet sauce drenched chicken? It's great. Unless they don't keep the food at the proper temperature, or it gets old and then it develops some nasty growth that leads to food poisoning. In this event, when you get food poisoning after eating some food that you don't eat on a daily basis, you form a very quick and strong association between sickness and the food. And when someone asks you, would you like to go get Chinese, you're not very likely to say, oh yeah, let's definitely go hit the Chinese buffet. You'll have a slight aversion to it. Of course, this goes away over time. I've developed a few aversions in my day to Chinese food, to Mexican food, to Greek food. It all goes away. But this is classical conditioning. You pair this foreign food with extreme intestinal discomfort, and then you begin to associate the food itself with the discomfort, when really it wasn't the food. It was some sort of probably bacterial growth in it that led to this. But that's all classical conditioning is. All right, it's a very passive form of associative learning. We're associating two things together. Here's Pavlov's dog in cartoon format. The first thing we need to distinguish would be a stimulus versus a response. A stimulus is something that's eliciting a response. A response is something that the animal does after it's presented with a stimulus. All right, so cause and effect. The stimulus is the cause, the response is the effect. Okay, now we have conditioned versus unconditioned. When we hear conditioned, we should think changed, right? Like the air conditioner changes the air. Unconditioned, no changing. We could also think of conditioned as learned. So the conditioned stimulus is the learned stimulus, the one that we have to ascribe meaning to. It's meaningless at the beginning. The unconditioned stimulus, however, requires no learning, requires no change. It's a meaningful stimulus that we respond to in a known way. For example, food, shown as a burger in this cartoon, is going to lead the dog to salivate. Dogs salivate in response to food, so do we. Animals salivate because it's one of the first parts of digestion. All right, getting the digestive enzymes in your saliva to start breaking down the food along with the mastication there. Now, by pairing that conditioned stimulus, all right, that's what that little blip up in the line means. By pairing the conditioned stimulus, the tone, with the unconditioned stimulus of the food, This is going to cause the dog to associate the tone with food and thus salivate in response to the tone alone. So the salivation that's in response to the food is natural. It's unconditioned. It's an unconditioned response. But over time, the dog will learn, when I hear the bell, that means I'm going to get some food. And so then you can produce the conditioned response of salivation in response to the bell alone. And that's it. Now the dog has learned. Bell means food. We learned this same thing. We learned that bell means get up and leave class. If it's around lunchtime and you hear the bell, bell means food. Classical condition will also work for emotions. There's a famous study on little baby Albert. He was conditioned to be afraid of white rats. When he was about 11 months old, he was enrolled into this study. And then by pairing the white rat with a very loud noise, this fear developed. He was conditioned to become fearful of the white rat, and this generalized to similar objects. Let's have a look at the experiment here.
In the early part of the 20th century, psychologists John Watson and Rosalie Rayner set out to teach a baby boy called Little Albert to fear white rats using the principle of classical conditioning. This is a film of their work. The film shows several phases of their study. First, as you see here, the investigators demonstrated that prior to conditioning, Little Albert had no fears of any animals, including, of course, white rats.
All right, what you should notice here is that little Albert isn't responding negatively to any of these animals here. All right, even the rat, which some adults are very afraid of. This is a lab rat. They're very tame. And you can see this applies to multiple animals here. Dogs, rats, rabbits. So he's not crying. He's not trying to move away. No fear.
Watson and Rayner then sought to teach Albert to fear white rats through classical conditioning. In the conditioning phase of the study, which was not filmed, the investigators struck a steel bar with a hammer whenever Albert reached for a rat, making a very loud noise that greatly upset and frightened Albert. After 6 such pairings of the loud noise and the rat, it was believed that the boy had been conditioned to fear white rats. That is, Albert was now expected to react fearfully to white rats whether the rats were paired with loud noises or not. In this next film sequence, we see Albert interacting with a white rat after the conditioning process. The investigators believed that the child's reaction during this trial demonstrated his newly acquired fear of white rats. Finally, the investigators expected that little Albert's conditioned fear of white rats would generalize to stimuli that were similar in key ways to a white rat. In this film segment, they were trying to demonstrate that the child now also reacted fearfully to similar objects, such as a rabbit, a dog, a furry object, and a white mask worn by Watson himself.
So in this case, little Albert seems a little less happy. You can see him crying in some cases. Their interpretation here is that he's developed an aversion to things similar to the white rat, and as such, he responds fearfully to similar objects. All right. He didn't have any fear for wooden blocks. Things of that nature. So here they believe that they've demonstrated classical conditioning for fear in humans here. And we actually see this all the time. That's really all a phobia or a post-traumatic stress disorder is. I mean, at a very basic level, they're very similar. It's really classical conditioning. It's associative learning. All right, you'll develop a phobia to something if your amygdala becomes activated while you're exposed to that. So early on in life, if there's a fearful event, like when young Bruce Wayne was, uh, assaulted by bats, he developed somewhat of a fear to them. Okay, in the world of nonfiction, we also have these. Many people have spider phobias. Some people are afraid of clowns. Whenever you look at a spider or a clown, this is going to, of course, activate different portions of your cortex. Spiders look different than clowns do. You're going to get a distinct pattern of neural activity in your occipital lobe, all right, your visual cortex. So your neural representation of spider can be paired with amygdala activation. So if you're frightened, or if you're bitten by a spider, let's say, you can quickly develop an aversion to them, a fear, a phobia, if you will. So people with a phobia show very strong amygdala activation. Let's have a look at the fMRI data on the top. That yellow circle there is showing you the activated amygdala. So these phobic individuals were then put through some exposure therapy, where they were exposed to their fear in a non-threatening environment, and they unlearned this fear. So they essentially unpaired that cortical representation of whatever they're afraid of with amygdala activation, and they no longer had this phobia. When exposed to it, as you can see in the fMRI below, the amygdala is not activated compared to above. So if certain objects, if certain perceptions become paired with amygdala activation, well, this can create strong negative emotions, otherwise known as phobias. And this also is involved in post-traumatic stress disorder. So when you go into a similar environment or you hear maybe similar sounds that were occurring during a very stressful time, like wartime or some other traumatic event, this can reactivate your amygdala and cause the severe anxiety associated with these. Now, the way that we can unlearn these connections is through a process called extinction. So that association goes extinct. All right. The conditioned response could be salivation for Pavlov's dog, or it could be amygdala activation and fear. The conditioned response that occurs following the conditioned stimulus is only going to continue if they're paired with one another. If you start to have exposure to the conditioned stimulus without that unconditioned stimulus there, well, then you're not going to have the same response. The dog is not going to continue to salivate for the rest of its life every time it hears a bell. It's going to also learn that the bell doesn't mean food anymore if the bell is presented alone repeatedly. Now, this extinction isn't complete or permanent. Sometimes you'll see spontaneous recovery when you're studying classical conditioning in animals. All right, whenever we work through our phobias, sometimes they will come back briefly, and after extinction, it's also much easier to recondition. So once the dog unlearns this pairing, you can quickly recondition it by pairing the tone with the food, and that'll lead to much faster learning than it had initially. All right, let's see if we've gotten anything out of this. Go ahead and pause the recording, and then we'll answer these in a moment. All right, so let's work through this first one. Describe how learning occurs during classical conditioning. All right, so we should remember conditioned is all about change or learning, and a stimulus elicits the response. So in classical conditioning, we take a neutral stimulus, that conditioned stimulus, and we pair it with an unconditioned stimulus, one that's meaningful to the animal. Let's use Pavlov's dog here as the classic example. So we're going to pair a tone, that's the conditioned stimulus, with food, that's the unconditioned stimulus. Food is going to give us an unconditioned response of salivation. When you give a dog food, it salivates. It begins the process of digestion. By pairing the conditioned stimulus with the unconditioned stimulus, the dog creates that association between tone and food, so that after several pairings, the tone alone, the conditioned stimulus, is able to elicit salivation, which now is a conditioned response. Notice salivation is both conditioned and an unconditioned response, depending on the stimulus that's eliciting it. So both stimuli are going to give us the same response after the association is formed. Okay, now let's say that we go to the carnival as a kid and we experience some strong negative emotions. Maybe we stub our toe, or our parents are fighting, or who knows what's going on in the mind of children, but you become angry or fearful, or you have strong negative emotions, some amygdala activation as you're surrounded by clowns. This could lead to the development of a phobia, because when you're looking at those clowns, the only reason you know that they are clowns is because they elicit a distinct pattern of cortical activity that says clown. They usually have some white makeup on their face, usually some big red lips, big red nose, usually very pronounced eyelid makeup, probably a wig, maybe some big shoes. You know what a clown looks like, and so does your brain. So that clown neural network is activated at the same time as our amygdala. And as we're going to see in the next lecture, that pairing of activity between these regions of the brain causes them to form a strong association with one another. And so now when you look at clowns, even though it wasn't the clowns that made you fearful or angry in the first place, subsequent appearances of clowns might be sufficient to reactivate that amygdala because of the association that you formed. It's classical conditioning, it's neuroplasticity, pretty much the same thing. More on that in lecture 8. Okay, let's go to operant conditioning. All right, a little bit more of the same thing, but now it's a little more active. This is not passive learning. All right. In operant conditioning, we're shaping behaviors that we have control over. We don't choose when to salivate. We don't choose when to be fearful. These are passive events. Operant conditioning is all about using reinforcers or rewards and punishments to increase or decrease the likelihood that a behavior occurs. All right, we should remember this from lecture 1 when we talked about behaviorists. They use these things called Skinner boxes to study operant conditioning. So they had things like little levers or wheels that rats can spin. They also have a little metal grate on the bottom where they can deliver electrical shocks. So they're going to use reinforcers and punishments to shape behaviors. Now, reinforcers or rewards are pleasant stimuli. And then punishments would be negative. All right. Now we have a couple different types of reinforcers and punishment. Reinforcers are always going to increase the likelihood of a behavior. Punishments are always going to decrease the likelihood of a behavior. All right, and so the law of effect on the bottom there is saying that the likelihood of a behavior occurring depends on the ratio of rewards and punishments. If you do something and it leads to reward, you're going to do it. For example, if you're crying in the grocery store because you want a candy bar and then mom gives you the candy bar, you're going to cry in the future. So for all you current or future parents out there, when your child cries because they want something, don't give it to them. You're giving in and you're only asking them to cry in the future. Simply tell them no. If you want to be more forceful about it, you can provide a punishment in response to their crying. Remove something, take something away when they whine. Okay, so let's go over this positive versus negative. We got those 4 things up there: positive reinforcer, negative reinforcer, positive punishment, negative punishment. Remember, reinforcers increase the likelihood of a behavior. Punishments decrease it. Now, positive doesn't mean good. Negative doesn't mean bad. Positive means adding. So a positive reinforcer is when we're adding some sort of pleasant stimulus. Giving the rat food. Giving the kid a candy bar. So when they cry and you give a candy bar, that's positive reinforcer. You can't blame them when they cry. It's on you. You've told them to cry. A negative reinforcer, it's still a reinforcer. It still will promote the behavior, but we're removing something. So we're going to take away an unpleasant stimulus. We might say, I won't make you do your chores tomorrow if you do this. That would be a negative reinforcer. You're trying to get the child to do something, and you're doing that by removing something that's unpleasant to them, like chores, or in the case of a rat, removing an electrical shock. Punishments decrease the likelihood of a behavior occurring. Positive punishments would, of course, positive means adding, so we're adding something unpleasant. So we're delivering a shock, for example. And negative punishment is when we're removing something pleasant. We take away food. Okay, let's have a look at our rewards in action here.
At last he hits the bar and gets an immediate reward. Has he learned? Will it take him as long to press the bar the next time? Although the animal still makes quite a few irrelevant responses, he presses the bar much sooner the second time. The occurrence of a single reward has strengthened the tendency to make the response of pressing the bar. Notice that the rat performs exactly the same response which was rewarded.
Okay, so what are we doing here? Well, we're adding something. We're giving the rat food, so it has to be positive. And in this case, it's something that the rat wants. This is increasing the likelihood of it pressing the lever. Every time it presses it, it gets food. So this would be a positive reinforcer. When you press lever, you get something you want. All right, let's have a look at this next example.
With this device, we can put a mild electric shock on the grid on which the rat stands. The shock is adjusted to be annoying, but not painful. Shock is on. Shock is off. Pressing the stirrup bar turns off the shock. Although the shock is not strong, you will see that it supplies enough drive to produce a radical change in the behavior of the satiated rat. He hits the bar, the shock goes off, and he's rewarded. He hits the bar and is rewarded again. After a few more trials, which are not shown in the picture, he has learned to press the bar quickly as soon as the shock goes on.
Okay, so what's going on here? When he presses the bar, are we adding or are we removing? Well, in this case, we're removing a shock. Okay, so we're removing something that's going to be negative. Now, you might think that it's going to be negative punishment because there's a shock involved, but no, this is a negative reinforcer because we're removing an unpleasant stimulus. It's a reinforcer because we want the rat to press that lever. Remember, reinforcers increase the likelihood of behavior. So this is definitely a reinforcer. The rat wants to press the bar because it hates the shock. Unlike before, it was pressing the bar to get something it wanted. That's a positive reinforcer. Now it's pressing the bar to get rid of something it hates. So it's a negative reinforcer. All right, because we're still promoting that behavior. Now we can promote a lot of different behaviors. Some very complicated. Here's a monkey riding a dog. It's going to lasso a goat. Monkeys don't normally do this. This is not an innate behavior. It has to be learned. And it's all learned by operant conditioning. We reward the monkey as it learns to wear the little outfit. When it learns to sit on the dog, we also reward the dog. When it learns to, let the monkey ride it and chase the goat, we reward the monkey when it learns how to lasso. So we take these sequential steps where we have the monkey start to approximate the behavior we want. All right, that's what we call shaping. This is how we teach dolphins to do tricks. This is how we teach our dogs to do tricks too. Dogs don't innately roll over and play dead when you go bang at them and pretend like you shoot them. They learn that. And they don't learn it all at once. You first learn, Okay, lay down when I do this. Okay, now lay down and go on your side. Okay, now lay down, go on your side, and then your back. Right? We shape their behavior. So dogs, dolphins, monkeys, humans, all right, our behavior is going to be shaped with operant conditioning. Now, the way that you shape behavior matters. Right? The fastest way to teach an animal, whether it's a human or not, is with a continuous reinforcement schedule. So that means every single time a behavior occurs, it's rewarded. We reinforce it every time. When your dog sits, it gets a treat every single time. You get very fast learning, but you also get very fast unlearning because the animal expects the reward every time. So what you should do when you want a long-lasting behavior that you don't have to give a treat every time is start continuous and then move to an intermittent reinforcement schedule. And that's what we're seeing here with this dog. He has to wait. He has to wait a certain amount of time, a certain interval of time before we give him this treat. That's a part of his trick. So it could be a fixed interval. For example, after 3 minutes when you perform this trick, I'll give you a treat. And then later on, okay, after 5 minutes, the first time you perform the trick, I'll give you a treat. Or it could be variable. It could be anywhere between 2 and 4 minutes. Okay, so it doesn't have to be fixed. Now that bottom part there, right, fixed versus variable makes sense. Ratio versus interval. Ratio means the number of times they do the behavior you want. For example, you might tell your kid, if you clean your room today, then we'll go get some ice cream. All right, so the ratio there is they have to clean their room once and then they get ice cream. Then you might say, all right, if you clean your room from today until the weekend, maybe it's Wednesday, Thursday, and Friday, then we'll go get ice cream on Saturday. Now they have to do the trick of cleaning their room 3 times. All right, and then you start to make longer schedules of you have to clean over the course of a whole week. Then there's maybe a monthly allowance built into it. Okay, so ratio is the number of times they do the behavior, and then interval would be an amount of time that has elapsed. The point of all this is to spread out the number of rewards so that they're not getting rewarded every time, so they start to carry out the behavior without needing that reinforcer. And they don't always need the exact reinforcer. You don't always have to give a dog a piece of food like this lucky dog is about to get. This is what we call a primary reinforcer. These are things that we and other animals naturally like. Food. Food is great. Water is also pretty good. Removing pain. Nothing likes to be shocked. Okay, but you don't always have to use these. You can use classical conditioning to have the dog associate this treat with a clicker. You can use a secondary reinforcer, and a lot of trainers use this. They'll use a little clicker to tell the dog to do what they want, and the dog will do it because it knows that clicker means I'm going to get food eventually. So I'm going to listen to the clicker, I'm going to do the tricks, and I'll get my food. This is the same reason that we have jobs. We work for our paychecks. Your paycheck does not feed you. No one eats their paycheck. No one builds their home out of their paychecks. It's a secondary reinforcer. We want the paycheck, we want the money, because we can use that to buy things that we actually like. Food, water, homes, entertainment, right? Those primary reinforcers. Money and clicks, those are just secondary reinforcers that we learn through classical conditioning. Now, the way that this works is of course, through the activation of different parts of your brain. Now, what I want to highlight here would be dopamine. All right, we should remember dopamine from our lecture on consciousness when we talked about drugs like cocaine. Cocaine is highly addictive because it leads to the release. Well, it leads to an increase in dopamine levels by blocking reuptake. All right, amphetamine will lead to the release and block reuptake. Either way, by elevating the levels of dopamine, this causes us to believe that the behavior that we just did was really good and we should do it again. And this is why people become addicted to cocaine. All right, so a couple of structures that we need to get in our head here. There's this bundle of axons called the median forebrain bundle. So the medial forebrain bundle is going to actually release dopamine throughout our brain. And one of the sites that it releases this dopamine would be the nucleus accumbens. This is that part of the brain that gets depleted of dopamine receptors in cocaine and methamphetamine addicts. The nucleus accumbens is the part of our brain that determines reward or causes the expectation of reward. The jury's still out on this, but it's certainly associated with reward to some degree. So when you have an increase in dopamine in your nucleus accumbens, you think, that was good, I'm going to do it again. So when you receive rewards, like food, for example, that food is going to stimulate the release of dopamine. And so whatever behavior led to that reward, whatever behavior led to that dopamine release, we're more likely to carry it out in the future. Now, what about those punishments? Well, obviously this is going to go back to the amygdala. Negative emotions, it's all about the amygdala. When you receive pain, when you get shocked, this activates nociceptors, those pain-sensing neurons that we discussed previously. Those nociceptors are going to activate the amygdala. All right, so is stress. So anything that leads to pain or stress, worry, things of that nature, the nociceptors and the norepinephrine and the stress response, those are going to activate the amygdala. So punishments. If a behavior leads to punishment, it's probably something that's going to cause us pain or stress, and thus it activates our amygdala, and we think, this sucks. I'm not going to do this again. So when you get rewards, you get dopamine release in the nucleus accumbens, and you say, this is great, I'm going to do it again. Yes, I'm going to go do a bunch of cocaine because that leads to dopamine release, and that's a good thing. Don't do cocaine, by the way. Whenever you carry out a behavior that leads to punishments, that's going to lead to amygdala activation. You're going to say, this sucks. I don't like that. I'm not going to do that again. If you're a reasonable human being, that is. All right, let's see if we got anything out of this. Go ahead and pause the recording, and we'll handle these soon. Okay, so let's describe how learning occurs during operant conditioning. Unlike classical conditioning, these are behaviors that we can actually control. All right, we're not talking about something passive like salivation. Here it'll be things like cleaning up your room, going to work. Whether we do something or not depends on the rewards or punishments that behavior leads to. We're trying to maximize rewards and minimize punishments. Right? That's what it's all about. Now, keep in mind we're all snowflakes, so what's a reward to one person might be a punishment to another. But in the end, it's still all about maximizing our subjective rewards and minimizing our subjective punishments. Okay, now depending on when we get these rewards, that is going to affect the rate at which we learn. That continuous reward schedule, that gives us fast learning, fast extinction. All right, whenever we have some sort of break, some interval between each reward, we learn a little more slowly, but we unlearn more slowly too because we're not as reliant on the reward to carry out the behavior. So by going from continuous to some sort of interval schedule, that can help us learn quickly and then hang on to what we've learned. Okay, so rewards and punishments, reinforcers and punishments. Reinforcers always lead to an increase in the likelihood of a behavior. Punishments always decrease the likelihood of a behavior. So when we're talking positive rewards versus negative rewards, both of these are increasing the likelihood of behavior. Positive rewards do so by adding something pleasant, like food. Negative rewards increase the likelihood of a behavior by removing something unpleasant, like a shock. Positive punishments decrease the likelihood of a behavior by adding something unpleasant, like a shock. And then negative punishments decrease the likelihood of behavior by removing something that we enjoy. Okay, and so this reward and punishment, these are of course created in different parts of the brain. Reward is created by dopamine release in nucleus accumbens. Then punishment is created by amygdala activation from nociceptors or from the stress response. So if you do something and it leads to a whole bunch of stress, I would hope that you'd be less likely to do it in the future because of that strong amygdala activation that should occur. On the other hand, if you do something that's particularly rewarding, I would think that you'd be more likely to carry that out. If you do something nice for your partner, and he or she is very kind to you afterward. If you catch my drift, this will lead to dopamine release, and you're more likely to carry out that behavior. So get some flowers for your loved one. Stimulate some dopamine release. All right, now there are other forms of learning out there. It's not just about conditioning. Sometimes we actually have to pay attention and study material in order to learn it. We're going to start off with passive learning, this latent learning. Latent learning is a form of learning that occurs but does not show itself or manifest for some period of time. We believe that this exists because of a classic study shown here on the right. All right, let's have a look. We're looking at rat navigation through a maze. Now, rats can learn how to navigate mazes, and they do so more quickly when they're rewarded than when they're not. So look at those two lines that I've highlighted here. You got the not rewarded one. On the y-axis, we're looking at the average number of errors. So the amount of incorrect turns that the rat took in navigating the maze. You'll notice the rats who were never rewarded with food at the end of the maze didn't seem to navigate it very well. So you could take this to mean that they didn't learn how to navigate the maze. The other option here is that they just didn't care to navigate the maze. Maybe they did learn it. Maybe those rewarded rats, that other line that I've highlighted, the one that goes low much more quickly, the one that has the very quick reduction in errors, maybe they were just more motivated to show that they'd learned. Maybe there's really no difference in the amount that they've learned. All right, so to test this, what Tolman's group did was start rewarding the not rewarded rats, a different group of them. They rewarded them at 11 days. All right, so after day 10, these rats here started getting rewarded. Now look at that. Look at day 10 and before. There's still a substantial number of errors. They haven't deviated from the not rewarded rats at all, but as soon as they start getting rewarded, look at the rate at which their error number reduces. Now that they know that there's food at the end of the maze, yeah, they'll navigate it quickly because there's an incentive to do so. So the interpretation here is that the rats, they learned, they just didn't show it. As they were navigating the maze, they created these cognitive maps, they call them. It just means a map you build in your head of their surroundings. And they had no reason to navigate quickly until they were given the food. Now these cognitive maps, while they might sound like they're made up, no, these are actually real things. We create cognitive maps in our hippocampus. And the hippocampus is a very important structure for learning and memory, as we'll see in the next lecture. Within our hippocampus, we have neurons called place cells that become active when we are in specific places, called a place field. Let's have a look at this cartoon on the right, and this will explain how those cognitive maps worked in Tolman's experiments. So part A is showing you just a very simple cartoon schematic of the activity in 4 different place cells as a rat walks along a straight line. All right, you can see here that place cell number 4 becomes really active at the beginning. And then a little bit later, place cell 2 becomes active because the rat's in a different place. And when the rat continues to walk further down, well, cell 1 becomes active, and then cell 3 becomes active at the end. So there are different cells that respond to different positions in the world. As crazy as that sounds, it's true. The actual data for 80 different place cells are shown in part B. You can see there are a few place cells that are active pretty much everywhere, and they have a few hot spots. So the black or blue color means no or minimal activity, and then the yellow and red colors are showing you a very robust activation of the place cells. So if you look in the first column, second row, that place cell is active pretty much all over the entire grid that the rat ran on. You know, there's some red areas that were more active, but it's generally active, unlike the place cell above it, which is only active kind of in one spot. And if you look in the first row, second column, well, that place cell is silent. It didn't respond to any of these places. As you look around, you'll see that each of these place cells has its own unique pattern of activity. So when you pick any location in the cage, the rat knows where it is by looking at the activity of not just these 80 place cells, but all of its place cells. And based on their degree of activity, it keeps track of where it is in the world. Now you see changes to the hippocampus as we navigate the world more or less. For example, taxi drivers who have to navigate pretty frequently have altered hippocampi. Their hippocampi change over time. They have a much larger posterior region, and that's where you find more of the place cells. So their place cells expand because they need to navigate more than your average Joe. All right, this study was done long before we had GPS, so nowadays this effect is probably absent if we're using GPSs. But you know, as one thing grows, others must die off. So the anterior regions of the hippocampus, where emotional processes are being handled, those are actually a little smaller in taxi drivers. So if you ever get in a cab and it's an old school cab, driving around without a GPS, and he's a little blunt, he or she is a little blunt, don't hold it against them. All right, their hippocampus has changed. Their posterior region's a little bit bigger so they can navigate, but this came at a sacrifice. There's a little less emotionality going on. Now we also learn by modeling. We learn by observing others and copying them. All right, monkey see, monkey do. Humans are really good at this. In fact, we're much better than monkeys. It should be human see, human do. But this is observational learning. It's called modeling. We see someone do something and we say, all right, I'm going to do that too. All right, and children begin learning through modeling when they're about 12 weeks old. The images on the right are from the famous Bobo doll study, where they videotaped an adult beating up this little doll. It has sand on the bottom, so it rocks back and forth. You can sit on it and punch it to hold it down. You can throw it. You can use weapons on it. And depending on what video the children were shown, they were far more likely to carry out those actions that they saw the adult do on the Bobo doll. So if they were shown a video of the lady sitting on it and hitting it, well, then they would sit on the Bobo doll and hit it. Now, this observational learning is something that goes on in our educational system, particularly in medical school. Okay, if you're going to learn how to perform surgery, it helps to watch someone do it who knows what they're doing. If you go work in a lab, someone's going to train you and show you how to carry out different lab techniques. You're going to learn by observational learning, and then you're going to try it yourself. So by modeling, we get this kind of low-risk form of learning. We can also teach others after we've learned through observational learning. So we create what we call a diffusion chain, where after you learn a behavior, you then demonstrate it for others to learn. And then this is how knowledge can get passed down. It's just a term that people have ascribed to this very simple concept. Once you learn something, you can teach someone else. That's all a diffusion chain is saying. Now, how does this work? How do we learn by observational learning? All right, we create those cognitive maps using place cells. Well, we have mirror cells or mirror neurons that respond when an action is carried out either by ourselves or someone else. You see a similar pattern of activity. So let's look at the brain activity on the top, on the right there. We have two rows. The top row is showing you brain activity when the participants actually reached for something, when they executed the reaching action. So when they reached out for an object, the yellow and red areas became active. When they watched someone else reach out for an object, the yellow and red areas became active. Now, sure, there are many differences between the top and the bottom, but there are also some important similarities. And those regions that are active both when executing and observing an action would be what we call mirror neurons. Sure, it's fMRI, it's a very gross level of signal, but mirror neurons are what allows us to kind of keep this action in our head so that we can carry it out in the future. So if you watch someone perform some action, grooming themselves, or just making silly faces, like we see on the bottom there. So when the guy sticks out his tongue, well, this is going to activate mirror neurons in the baby. And this is going to allow the baby then to copy that behavior. And he sticks out his tongue. You can see when he opens his mouth or when he purses his lips, baby responds similarly. So this is probably how we, one of the ways that we're learning through just modeling, through observational learning. We watch, our brain holds on to that pattern of actions that we just saw someone else do so that we can try to execute it ourselves. Now this probably also applies to some degree to emotions and might help us explain empathy. When we see someone who's sad, we can feel that sadness because we'll see the characteristic changes in their face. We may see them cry, may hear them sound sad, and that's going to, of course, activate our mirror neurons. Some more so than others, of course, but this might explain why whenever we see someone else in pain, we can actually feel their pain. Of course, not to the same degree, but we can at least have a little empathy. Alrighty, let's wrap this one up. Go ahead and pause this, and then we'll knock these out in a moment. All right, so cognitive maps, those are brain maps. That's all they are. They're maps that you create in your head of the world around you. And the cells that create them are place cells in the hippocampus. As you navigate the world more, you're going to promote the growth of place cells, and you'll modify your hippocampus. Okay, mirror neurons. Those are the neurons that are activated when we see an action taking place or when we execute it ourselves. So these are the essentially mental practice whenever we see someone else do something. Like when we see someone else open a child-proof bottle of aspirin. We say, oh, that's how you do it. Okay, now I can do that myself. We see someone shaving, and then we learn from Dad how to shave ourselves. Oh, okay, you put the foam on, and you hit it with the razor. This is from mirror neurons. They keep track of what the other person did, allow us to hold on to that, and then execute the action ourselves. This applies to behaviors like surgery or a lab technique or grooming yourselves. It can also apply to emotions. So when we see their face change and look happy, well, we'll also feel a little bit of happiness. This is probably, to some degree, why you get a lot more laughter. You're more likely to laugh if you're at a comedy show surrounded by people laughing than you are if you're just watching the same show at home by yourself. When other people around you are laughing, that's going to activate your mirror neurons, and you'll essentially be laughing in your head, making it more likely for you to laugh. This is also why yawns can be contagious. When you see someone else yawn, your mirror neurons become active, you're more likely to yawn. Doesn't work every time, all right? Some of us have a little more empathy than others, but still, the mirror neurons are going to hold on to actions that other people perform or other emotions that other people have, and essentially play them out in our head. All right, that about does it. Email me if you have any questions. Otherwise, I'll see you for Lecture 8.